Hello everyone, my name is Parag and welcome you all in my new video. Okay, and in this video I'm going to teach you exactly about the design of the cantilever balcony slab. Okay, this is what the diagrammatical representation what you have seen over here. Okay, this is the D. Okay, this is what exactly the D. Okay, so we have to design this parameter wall. Okay, in the numerical 1.2 meter length, this means which is what parameters parapet wall, parapet slab, what this section you are seeing over here. Okay, this is what the parapet slab. Okay, so we have to design this parapet slab. Okay, so here the word W, that means this is the parapet wall as I listed over there, and the W, that means the parapet wall load acting on the edge, right? So the parapet wall height is a 19 centimeter and the thickness is 10 centimeter. Okay, and for the slab thickness, that means parapet wall thickness, parapet slab thickness is we cantilever is assume as a 80 mm assuming. Okay, so we have superimposed load or live load as a 2.5 kilonewton per meter square. Floor finish is a 0.5 M20 grade of concrete, that means FCK is 20 Newton per mm square and Fy is a 4 and 5 Newton per mm square. Length is 1.2, so I converted in mm. Right now, in this numerical, I'll explain you the total in detail. So the numerical in such a manner: design a cantilever balcony slab projecting 1.2 meter from the face of the support. That what does it mean? That it is projecting from the face of the support. That means it is projecting from this side, face of the support. Okay, and always it in such a manner. Now the superimposed load of the 2.5 kilonewton per meter square, as we write down over there. Okay, floor finish 0.5 kilonewton per meter square, M20 and Fe4 and 5 steel we are going to use. Length of the slab is given as 1.2 meter. Okay, and the thickness of the parapet wall is 10 centimeter and the height is a 19 centimeter. Okay, so now we have to design this cantilever balcony slab. So in this part 1 I am going to discuss with you the calculation of the effective span, the calculation of the factored load, okay, calculation of the factored bending moment, and the check for a bending criteria. This some part are these are going to covered in this video. So please, if you don't yet subscribe my channel, so please subscribe it. Okay, and visit my website www.civilnotes.com. okay, as you see you at the top. Okay, so please visit on this website and please subscribe my channel. Okay, I need your friends, please help me a lot. Okay, now so let's start with the numerical. First of all, I'll explain you how exactly this thing are going on. So for my step number 1, okay, my step number 1 is in a different manner. I'm going to solve in a different parameter wall, different parameter. I use my own steps. So my first step is that the assumption of depth, assumptions of depth from deflection criteria. Okay, from deflection criteria. Okay, so what we have to do, we have to determine for the we have to assume some depth of the deflection criteria. So it is in a simple manner that I always this is our first step, where the L upon that means basic value multiplied by modification value we have to take. Okay, so basic value for the simply supported beam is different, and for the basic value for the cantilever slab is 7. So L we have right now is as a 1200, which is I converted in mm, divided by it is 7, multiplied by the modification factor for the cantilever slab is taken as a 1.5. So we get the answer is as a 114.3 mm. Okay, so this is what D we got. Okay, after getting, we are the assuming the clear cover. Okay, assuming the clear cover. Okay, so this is a clear cover for the this cantilever slab. We taken it as a 15 mm. Okay, so we take it as a 15 mm. Okay, after taking the as a 15 mm distance, 15 mm as a clear cover. Okay, wait a minute, I'll just okay, after taking as a 15 mm. Okay, now after that and we have to assume also, and we have to take 8 mm dia Okay, we have to take 8 die also for a steel rod. Okay, so now after getting this value, whatever the D we are getting right now, it is the your total D we got plus clear cover. Okay, plus what is the diameter. Okay, and diameter divided by 2. So we have to put all the value. So it is a 114.3 plus the clear cover what we taking the 15 plus 8 by 2. Okay, that means 4. So we got the value is as a 11133.33. Okay, this is what the value we are going to. So we are getting round up and we take it as a 140 So the effect, the total depth, okay, it taken as a D. So this D is nothing but, okay, wait a minute, this D, okay, where it is, okay, this D we got. Okay, now after getting the D, we are going to solve in different, we are going to solve our next step. Wait a minute. Okay, now we got the D. After getting this D, now I determine the effective depth. Okay, the effective depth is very simple to determine. Whatever the depth you got, that means capital D minus of the clear cover minus of the L by 2, minus of the D by 2. Okay, so we have to take minus of the your clear cover minus of the 8 by 2, that means diameter divided by 2. Okay, so we got the value, it has a 121 Okay, this is the first step in a design of the slab always. Okay, now after getting this value, we have the capital D, we have the small d. Now this is what this d which is used for the design purpose only. Now we can determine the required depth, required design depth also, but according to this d and this effective d, we are going to design our cantilever slab. Okay, now the main thing is that the cantilever slab is having the section in such a manner, that is, it is fixed from one end, the load is acting on another end, and this is water line. Okay, or maybe it may be acting as a uniformly distribution load also over there. Okay, it may be happen like this. Now the main thing is that after getting the all the D, we are going to our step number 2. Okay, Mr. Arjun McCullough, okay, is if it's it is not going to see to anybody else. Okay, we take the blue. Okay, so the main thing is that we are going to calculate the effective span. Calculation for effective span. Okay, so when we go into calculation for the effective span, the formula is like LE we are providing for the effective span. The formula is L plus D by 2. Okay, so formula, just put the value 1.2 plus what is D we took 121 right now. So 121 divided by 2, so we get the value it as a 1.26 meter. So effective depth we got as a 1.26 meter. Okay, after that my step number 3 is here, where I just calculate the load condition. Now up to this two condition, I got a effective span, I got a dimension. Now I just go for a load calculation. Okay, so I just go for the load calculation. Okay, so in the load calculation, my first step is to determine the calculation of the factored load. Okay, so calculation of the factor load consists, that means W, and we have to take factor, so it is WU. Okay, so after that, in calculation of the factor load, the first thing is that you have to determine the self weight of the slab. Okay, so self weight of slab is very simple because it is given by BD into gamma. But in this condition, B we know, okay, D is nothing, is taken as D plus the thickness of the at another end, which is 0.08, we assume it as a 80 centimeter. Okay, the 80 mm divided by 2, okay, multiply by unit weight gamma. So it is like, why I take 0.08, okay, why this formula come like this? So it is like this parameter. Okay, so this is what 80 mm, okay, and here the D is here, total D, which is we calculate as a 140, and this is what L. Okay, so if you want to determine the self weight of this slab, we have to take B D into gamma. Okay, so this is what here, so I just take all the value over there. Okay, so calculation is in such a manner that I take b as a 1 plus d depth is, we know that is it is 0.14, you can see them because we take in meter, so 0.14 plus 0.08, okay, divided by 2, okay, multiply what is a gamma, that means unit weight is for a concrete is that means steel plus concrete 25, only for concrete it is 24, so we get the value 2.75 kilonewton per meter. Okay, after that we have to just go for a next step. Wait a minute, let me take all this value at upstairs. Okay, now second step is that where we have to calculate. Okay, after doing this value, we have to further proceed for the floor load. Okay, so it is for FL. Okay, it is for floor load, so it is in a such a manner that what is the 0.5. okay, we have to, it is 0.5 kilonewton per meter. Okay, and third load is what the live load. Okay, so live load is nothing but what we have 2.5 kilonewton per meter. Now the total load what we got, that means the total load we have, which is a W, is taken as 5.75. how the 5.75 kilonewton per meter come, like 2.5 plus 0.5 plus the load of the self load is 2.75. okay, which is this load, you can see over there. Okay, 2.75, so we got 5.75 W. Now we have to make factor loading, so it is really very simple, that WU we get in a simple manner like 5.75 multiplied by 1.5, right? So this value we get in such a manner, like we get the value as 8.63 kilonewton per meter. Okay, so this value we got. Now so it is what we got a WU. So after getting this WU, we are going to solve our next step, where since there is a parapet wall at the free end, hence there will be a concentrated load also, so due to it will act as a center of gravity of the parapet wall. Okay, so because of, actually you can see that, okay, at the at this side now. Okay, you just find out that here oh sorry, my this is not properly taken. Wait a minute, I'll just take my position in proper manner. Okay, so here you can see, okay, the parapet wall in such manner, okay, it is fixed, and here one loading also connected. So because of that, it is act as a concentrated. So since there is a concentrated load, so we have to also determine the concentrated load due to the parapet wall. Okay, so concentrated load due to parapet wall, so it become like this, that means it come like 1 multiplied by thickness of wall okay, multiply by height of wall, multiply by density, multiply by height, multiply by density. Okay, so we get it in such a manner that 1 multiply by, we have the particular, it's having the 0. That means 10 centimeter by 19 centimeter, you can see in the diagram. Okay, first diagram what I showed you, multiply by 0.1, multiply by 0.9, okay, and multiply by the unit weight for this is 20. Okay, so assuming density of the masonry, this is what the density of the masonry wall, density. Okay, so when we get calculate all these values, so we got as a 1.8, okay, kilonewton. So this is what we got as a W. Okay, when we make as a WU, so 1.8 multiplied by 1.5, 1.8 multiplied by 1.5, so we get value as 2.7 kilonewton. Okay, so this value we got. After getting this value, okay, so main thing is that the load is acting with the centric load is acting over there. So in the diagrammatic representation, if I show you how exactly it acting as, okay, so there is a two types of the loading is acting. Okay, the load is acting in the center, okay, and the load is nothing but this load 2.7 kilo Newton. Okay, this is what fixed support, fixed support. This is what the length L given to you. Okay, and also, and this is what L. Okay, total L. This is what effect L also. Okay. Now the total load, so we got the total load. Okay, so now after that, this 8 point is it is a load for a factored load for our cantilever slab, and this is what point load we got. Now after this situation, we are just go for our next step. Okay, so our next step in a such a in such a manner. Okay, wait a minute. It takes some time, guys. Okay, now how we can do it? So our next step is calculation of the factored bending moment. Calculation of factored bending. Okay, so calculation of the factored bending moment is very simple, which is given by mu. It is because of moment by mu. Okay, so we have the two load right now. This is one load, and this is another load actually there. Okay, right? Yes. So this calculation is done because of mu due to UDL. Okay, plus mu due to masonry wall or concentrated load due to point load, we can see that. Okay, so the calculation is such a manner that whatever the load is to be there, it is given by W into LE square by 2, plus that for UDL we take the effective length, because effective length is up to the this point, like for okay, up to this point, right? So and it is the difference, that is L minus LE हो जाएगा, LE. Okay, so now it is a W into LE dash. LE dash is nothing but this up to this level. Okay, this is what LE dash. Okay, so the put all the value, that means 8.63 multiplied by the length, effective length is 1.26 square divided by 2 plus 2.7 multiplied by 1.21. Okay, so we got the value as 10.12 kilonewton into meter. Okay, so this value we got. Okay, so we can just convert into 10.12 into 10 raised to power 6 Newton into mm. Okay, now after that we got the mu as 10.12. Okay, now we go for a check for a depth. Okay, so we go for a check for depth. Check for depth from bending moment criteria. Depth from bending moment criteria. Okay, so it is in such a manner that we are going to equate our mu with the mu limiting. Okay, so this equation tends to be in a such a manner. What is the value of mu is 10.12 into 10 raised to power 6 equals to 0.138 fck bd square, right? So it is fck bd square. Okay, so this equation tends to like this: 10.12 multiplied by 10 raised to power 6 equals to 0.138. What is the value of fck? Is nothing but 20 multiplied by 1000 multiplied by d square. Okay, so when we equate this value, we get the d as 60.55 mm. So this is our required d, that means required depth, where for which we have to, which is for required for a design. But what we got, what is our got d, that means effective depth we got is as a 121. So comparing with this value, our calculation is more, so our design is safe. Okay, this is our first check. Okay, after that the thus we are going to provide the calculation for doing for a 121. Okay, and for the capital D equals to 140. Okay, so for that our the calculation is set. Now for the further calculation of the design of main steel, design of the main steel, okay, and spacing and design distribution steel share modification factor, okay, it comes under the part number 2. So if you like it, and keep watching, keep learning. Have a nice day. Bye bye.